It's on page 9 of your notes. Again, weak acid, strong base. So I'm skipping the page before it. You can kind of look back at that if you'd ever need to, but here's what we got going on. In this case, the acid is in here, so here's our weak acid. My good flask, beautiful flask. Our weak acid, which is acetic acid, so there's our 0.2 molar, and there are 40 milliliters in there. So at the initial point, all we have is a weak acid. So here's our starting point. All we have is a weak acid, 40 milliliters. And it is 0.2 molar. So that's going to have a fairly low pH because all it's in there is weak acid. We're going to titrate that with NaOH. So our burette here has some 0.1 molar NaOH. Again, first thing I like to always do is figure out how many milliliters of this will take to get to the equivalence point. Now, usually when you're doing titration, you don't know one of these molarities, and you just have to figure out how many milliliters you add until you get to a color change. Then you can figure it out from there. Well, this is half as concentrated as that, so it's going to take twice as many milliliters of this to get to the equivalence point. Okay, everything's in a 1-to-1 ratio here. So if this is 40 milliliters, it's going to take 80 milliliters to get to the equivalence point. Or you could do MVMV. You could 40 times 0.2 equals M times 0.1, but it's going to take 80 milliliters to get to the equivalence point of our strong base. Let's write our reaction out here. Well, we'll write that out here in a second. So again, so let's figure out when we've added 0 milliliters of NaOH. Let's figure out what the pH is. Well, initially, all we have right here is strong acid or is weak acid. So we're going to bring back to get the pH of a weak acid or a weak base. We have, so if we have that in water, it's in equilibrium. Remember, not very many molecules are going this way. H plus C2H3 O2 negative. So remember, if we know this concentration is 0.2 molar, all we got to do is Ka equals x squared over 0.2 because it is a weak acid. So our Ka value we know is up here is 1.8 times 10 to the fifth. Again, this is before you add any NaOH into this titration. So cross multiply Ka times 0.2, take the square root, and that will give us x, which is, remember, our concentration of H plus in this case because it is a Ka value. And that concentration is 0.0019 molar. Hopefully my math is right. I did this in a big hurry. Take the negative log of that to get our pH, and our pH is about 2.72 to start with. So this pH is 2.72. That's all that's in there. Okay, now, obviously, there's a little bit of our conjugate base, but not very much because less than 3% of these dissociate. So a really small amount. There'd be that much of our conjugate base in there. But mostly just weak acid before we add any NaOH. Okay. So now we're going to start adding some NaOH. I'm going to make up a number. I'm going to just say, let's say we had 10 milliliters. I could have chosen 15 or something like that. 20. It's 80 milliliters to get to our equivalence point. So this isn't even halfway to our equivalence point, which we'll do down here. Let's go ahead and fill that in. So halfway to the equivalence point would be half of that. So that'd be at 40 milliliters. And then the equivalence point down here would be 80 milliliters. So I'm just making this up, this 10 milliliters, just saying, let's say we add 10 milliliters of NaOH in there. What do we have now? So first thing, let's write our reaction. Okay, draw the line here. So our reaction is our acid plus our strong base, OH negative, one-sided arrow. Okay, so as this reacts, it's moving completely that direction. Going to get water. So the hydrogen plus that, plus C2H3O2 negative. So let's think about this for a minute. Up here, all we have is weak acid before we add any OH. As soon as we add a drop of OH negative, one drop, we now have started adding some conjugate base. So now we have a solution that has weak acid and its conjugate base, which means we now have a buffer. Now, eventually we'll get to a point where all of this will be reacted off at the equivalence point. When we have equal moles of these two things, this will all be reacted off, and then we'll have only the conjugate base. But anytime in between there, we have a buffer. If we have a little bit of weak acid and its conjugate base, we have a buffer. So remember, our buffer equation is H plus equals Ka times the acid moles over the base moles. H plus equals Ka acid over base. So we'll use that whenever we have a buffer situation. So we need to know how many moles we have of this, how many moles we have of that. If they're equal, then obviously our H plus equals Ka. So for this, it's always 40 milliliters of 0.2 molar. 40 milliliters, 0.2 molar. So 0.04 times 0.2 is that many moles of our weak acid. Reacting with, so it's just stoichiometry here, OH negative is 0.1 molar, and we've put in 10 milliliters. So we have 10 milliliters, 0.1 molar. So 0.01 liters times 0.1 is 0.001 moles OH negative. So now it's just limiting reactant. 1-to-1 ratio. This is going to run out first. So we're going to go down by 0.001 moles of this. We're going to be at 0, essentially. Remember, there's always some OH negative in solution, but small amount. Minus 0.001 means we have 0.007 moles of, I'm just going to put our weak acid right there. Let's go to the other side. Some water's made. Not so concerned about it, but I do want to know how much of this is made. So it's going to go up by 0.001, so we're going to have 0.001 moles of what I'm going to call our conjugate base, C2H3O2 negative. So now we have a buffer because we have a little bit of this, a little bit of this. Not a real good buffer because we have a lot more acid than we have base. I like to have them be fairly equal, but we can plug into here. So our Ka, which is 1.8 times 10 to the negative fifth from up here, times the acid over the base, 0.007 over 0.001. Okay, that's just our acid over our base. There's our buffer equation. H plus equals Ka times acid over base. Remember, you cannot do the buffer equation up here when you have only the acid, because now you're going to have a 0 in one of these spots. We can't have that 0 in there. Concentration H plus, then if we multiply that, a concentration H plus is 1.26 times 10 to the negative fourth molar. Negative log of that, and we have a pH of about 3.90. Hope I haven't made any math errors. I did this, like I said, really fast before this video. So 10 milliliters, our pH went from 2.7 up to 3.9. It should have gone up a little bit. Makes some sense. Let's go down to halfway to the equivalence point. Move my sheet up here. So again, halfway to the equivalence point would be when we've added 40 milliliters of NaOH. Reaction's the same as it has been. We had our HC2H3O2 plus OH negative, making our water plus our conjugate base. Put the water over there in this case. Again, our moles of this is the same. Okay, so it's not saying we're adding 40 more milliliters. It's saying, okay, when we've added exactly 40 milliliters of this. So I know this is 40 milliliters of 0.1 molar. And this is 40 milliliters, 0.2 molar. So these moles, initially 40 times 0.2 is 0.008 moles. 40 milliliters, 0.1 molar is 0.004 moles. Remember, those are just our moles. And we're going to say that none of those for now. Stoichiometry, limiting reactants to this, so this is going to go down by 0.004. That's going to be 0. It's all going to get reacted off and make water and conjugate base. So think about this titration. A weak acid and a strong base. The reason the pH at the equivalence point is going to be higher than 7 is because we're going to have strong base at the equivalence point. I'm sorry, we're going to have weak base at the equivalence point. So weak acid, strong base make a weak base. So this goes down by 0.004. We have 0.004 left over. Remember, this is our weak acid. This had to go up by 0.004. That's our conjugate base. So notice we have equal amounts of weak acid conjugate base. That's the perfect buffer. So our H plus equals Ka times the acid over the base. 0.004 over 0.004. Remember, these are equal now. We have equal weak acid conjugate base, so H plus equals the Ka. Concentration H plus is the Ka because we have equal acid and base, perfect buffer. Negative log of that, our pH is about 4.74. At halfway to the equivalence point, the pH will equal the pKa. Halfway to the equivalence point, pH will equal pKa because you have equal moles of acid and base at that point in time. I'm not sure we'll do a past the equivalence point one, so we'll probably just do this last one right here. At the equivalence point, we have 80 milliliters of NaOH. Back up here. I usually ask you what things are present. Well, in this case, we have equal amounts of equal amounts of those. Okay, equal amounts of those. 0.004 moles, 0.004. In the one before, we had a lot more acid than we had base, 0.007 and 0.001 for those. At the equivalence point, so let's write the reaction out again. I'm going to erase this stuff up here. So our reaction again, same reaction spin, is HC2H3O2 plus OH negative same reaction got going. Sorry about the glare right in that spot. It's going to be a bad spot for it. I'll write a little bit lower than that. Again, this is 40 milliliters, 0.2 molar, so this is still 0.008 moles of our acid. This at this point in time is going to be 80 milliliters, 0.1 molar, which is also 0.008 moles. So both these are going to run out. That's the equivalence point means. You have equal moles of these two things. So going down by 0.008, going down by 0.008, 0, and 0. Those have reacted off. Well, that means that this, our conjugate base, has gone up by 0.008, and there's now 0.008 moles of that. So we no longer have a buffer. We don't have any of our conjugate acid, any of our weak acid with our conjugate base. We have only conjugate base. That's all we have, is just conjugate base. So in this right now, all we have is C2H3O2 negative, which is a weak base. So if you think about it, to get the pH of weak base, you have to do Kb equals x squared over the concentration of that weak base. Now we need to get the Kb value, which we can get from the Ka. So our Kb we can get over here, we can go 1 times 10 to the negative 14th divided by 1.8 times 10 to the negative 5th, which was the Ka value of the conjugate, which is 5.56 times 10 to the negative 10th. So there's our Kb value. We cannot plug this in because this is just moles. So we got to get the molarity of this. So we need to take our 0.008 moles divided by our liters, which in this case would be 40 milliliters, 80 milliliters, 120 milliliters, 0.12 liters. So we got to know that concentration in this case, which would be 0.067 molar. Now we can plug in. Kb equals x squared, so we have our Kb, 5.56 equals x squared over 0.067. I'm going to write that down here because I need space, but so 5.56 times 10 to the negative 10th equals x squared over 0.067 molar, because all we have at this point in time is that. Cross multiply, square root, remember x in this case is our concentration of OH negative. Trying to find this, and it is 6.1 times 10 to the negative 6th.